To understand what led up to Howard's work in 1802, we need to go back almost 20 years before that, to the very atmospheric year of 1783. That year, 1783, brought a very sudden change to the climate and our understanding of it. And it caused a panic to settle in the European mind, which had an influence on mineralogical thoughts. But it also had an influence on the mind of then 10-year-old Luke Howard, who had never seen anything like this, and gave real inspiration to his early ideas. According to most of the weather journals that have survived to tell the tale, the first few weeks of the spring of 1783 started out fair and temperate with a balance of cloudy and sunny days. As 1783 wore on, a new, unfamiliar pattern began to be widely noticed. Hot and foggy days were followed by cold and dark nights, with a hovering fog that seemed to shroud everything and did not disperse and got steadily worse. By June, a haze settled everywhere, canceling the sun, deflecting its light from even the clearest days. According to accounts from the time, the sun looked black and shone a rust-colored light upon the ground. Animals became restless, swarms of flies began to hatch, and food couldn't be kept fresh, and birds could not travel. Illness began to spread, people had trouble breathing and experienced headaches and nausea. Newspapers called this the thick, disagreeable mistiness, and remained unrelenting as it was unfathomed. The vapors of the evening brought on a new, disturbing vision, the aurora borealis, or the northern lights, or at least a displaced variation. This terrified the onlookers, whose latitude was too south for them to usually be able to see the lights. But night after night, the colors danced over the horizons, as Europe was hit by solar winds. For Luke Howard, this great cinema of light proved all that was strange about the air. By Howard's day, meteorologists had all sorts of instruments with which they could measure the weather. But the obvious limitation was that all these instruments were stuck here on Earth. And so increasing aspirational attention was paid to measuring these conditions of the sky. But a closer understanding required a closer approach. In answer to the problem that emerged was a pioneering form of flight, which was the first balloon, as seen in Paris at the end of 1783. Two French brothers, Joseph and Jacques Montgolfier, initiated the age of the balloon by essentially creating a convective current in a bag. They first sent up animals which all survived the ordeal, and soon humans would learn to fly among the clouds. The first manned balloon flight was in November 1783 and exerted a profound influence upon the European imagination. One such man, named Jacques Charles, known today as the framer of Charles' Law in chemistry, was an extremely enthusiastic balloonist who became the first man to see the sunset twice in one day. In the winter of 1783, Jacques Charles accompanied a balloon ascent, which lasted 2 hours and went up to a height of 3 kilometers from which they watched the sunset. When they touched down, he demanded that he be allowed a second flight the same evening, which he underwent alone, where he rose higher on the second occasion, bringing the sun back into view until he watched its second setting. It didn't take long for ballooning to find enthusiasm in British cities, and the use of balloons for meteorological research was exploited from the very beginning. In fact, the Montgolfier brothers sent a barometer in their balloon in order to record air pressure at great heights. The following year, an American researcher, Dr. John Jeffries, ascended in a balloon in London through which he took a barometer that was able to show extremely low pressures. He also took vials of atmospheric gas on behalf of Henry Cavendish, who was an English chemist. Cavendish was researching the gaseous composition of the atmosphere, which was the first to demonstrate that the lower atmosphere contains oxygen at a concentration of approximately 21%. That year, 1783, the Earth had been hit by major earthquakes and volcanic eruptions in Italy, Iceland, which sent plumes of gas into the atmosphere. Small eruptions, which happen every year, produce small amounts of material which fall to the ground and are dispersed. Particles of dust are always present in Earth's atmosphere as they perform a valuable function of screening the sunlight, absorbing radiation, and supplying condensation nuclei, which are necessary for cloud formation. The atmosphere around us is a mixture of gases, with about 78% nitrogen, 21% oxygen, and 1% of a mixture of trace gases, which include carbon dioxide, helium, and methane. And so this mixture is what gives the atmosphere all its weight, or at least 98% of it. The other 2% comes from water, which are clouds in the atmosphere, as well as dust that come from grains of sand or pollen or smoke from a volcano. Now, a great volcanic eruption will release a ton of ash and sulfur into the air, and this can have great effect on the climate. In fact, the sulfur will react in the air to form sulfuric acid, and when it precipitates, this will be acid rain, which can damage the crops and the soil. But sulfur in the air can also be suspended as a cloud for longer than normal clouds. And so this is what causes the sudden cooling and the discolored sun, as well as the haze and the fog and the terrible sulfurous smell. In 1782, eruptions in Japan began, which started to form a visible tropospheric case over the island. Later that year, another eruption in Japan was described as the most frightful eruption on record. The lava flows, mudslides, and ash killed 1,500 people right away, and it also blocked incoming sunlight, which resulted in what is known as the Tenmei famine, which killed over 300,000 people over the next several years. In Iceland, the volcano erupted in May and then another one in June, and continued its activity for several months. This added hundreds of tons of sulfuric acid into the air, which was distributed over northern Europe. By 1783, Scotland was completely covered in famine and crop failure, and mass poisoning of livestock ensued, and illness spread. The cooling effect was felt immediately, and the year became known as the Year of the Ashy, which re-radiated summer heat. The reaction to the weather of 1783 lingered long enough in the European mind to disturb it, and allowed for a wide transformation in thought about the weather during the European scientific Enlightenment. Most of the attempts to rationalize the study of the weather had errors and misfortunes. The first attempts to collect weather statistics just required a lot of resources to overcome all of these obstacles.
Duke Ferdinand of Tuscany was behind the first major weather monitoring project that ran for 13 years in the mid-17th century. He set up weather stations across Europe, but was eventually disbanded in 1667 and was shortly followed by Duke Ferdinand's death. Robert Hooke, the first curator of experiments at the newly instituted Royal Society of London, also tried to fix the problem of recording the atmosphere. He proposed a method for making a history of weather and producing guidelines for how to record it. But like other attempts to collect weather statistics, Hooke's ideas faded to nothing in the end. Hooke failed to capture the level of enthusiasm needed to keep such a project running effectively. Robert Hooke also attempted to create a language and classify the clouds in the style of other Enlightenment thinkers such as Descartes, but within months he had moved on to microscopes and pendulums. European science at the end of the 18th century was taken up with its encyclopedic projects of classification and naming of everything in nature. Travelers returning from voyages would bring new unknown species, and the search for meaningful patterns in nature was preoccupying the scientific mind. Earlier in the century, the Swedish botanist Carl Linnaeus had introduced a system known as binomial nomenclature to natural history, where every kind of organism could be designated by a pair of Latin names. This was hugely influential from the start and provided logical structure to naming the living world. The problem was that it insisted that species were permanent, distinct, and unchangeable, an idea we know today that does not hold up.
And so the goal of natural history became to find general relationships between individuals rather than describing all of the specifics. One such man was Jean-Baptiste Lamarck, who worked in the French Natural History Museum during a very turbulent time in European history.
The French Revolution was the overthrowing of the French monarchy and the establishment of the French Republic, which instituted a new scientific regime. Parts of this regime have survived, while others were later abandoned when Napoleon became Emperor of France and began a war in Europe. The measurement system of most of the world today comes out of the French Academy of Sciences, and was successful in creating a universal standard based on our closest approximation of the properties of Earth itself. At this time, Lamarck proposed a system that was the first to suggest clouds could be graded by altitude or height above sea level. However, Lamarck viewed clouds as individual entities rather than members of a larger species, and therefore he needed hundreds of words to describe clouds, a system that would never be easily adopted. But another reason for Lamarck's decline and Howard's rise was connected to war between France and Britain, due to Napoleon's expansionism. Rumors of Napoleon's colonial plans included the invasion of Britain by means of ships, tunnels, and the newer technologies of hot air balloons. In the end, the invasion of Britain never happened, but the country prepared itself for the worst.
So war and revolution dominated the background of how we classify the clouds. And in the 1920s, meteorologists at the Bergen School named the space of air between two air masses a front after the battle zones that had just occurred during World War I. In both cases, the front is responsible for a lot of violence, and in the case of the weather, that is where severe weather will occur, and therefore the imagery of battle was chosen to describe the weather.